Session is called Titled Collaboration, and we have very interesting 3 papers about collaboration in VR and AR. The first paper is from IBM Research Group, titled Immersive Insights, a Hybrid Analytic Systems for Collaborative Exploratory Data Analysis. And the authors are Marco Cavallo, Michel Dolaika, Matheus Havlena, Ken Ochtree, and Mark Podlesek. And we have today Marco as a presenter here. So Mr. Marco Cavallo graduated in computer science and engineering from Politecnico di Milano in Italy, and also University in Illinois, Chicago, which is renowned for cave systems in electronic visualization laboratory. He has been working at IBM Research in New York, where he worked on applications for AR and VR technologies for visual analytics in the context of data science and healthcare research. Recently, he joined Apple in California. He's currently working on data visualization for machine learning and computer vision algorithms. So let's welcome Marco. Thank you.
Okay. Thanks a lot for the introduction. So as Ken mentioned, today I'm going to be presenting a work that I did in collaboration with my former colleagues at IBM Research. The title is Immersive Insights, a Hybrid Analytic System for Collaboratory Exploratory Data Analysis. Let's go quickly to the definition of exploratory data analysis, which is, we could call it the process of performing initial inquiries on a data set, and the goal in this case is to discover interesting patterns, spotting anomalies, testing hypotheses, and checking assumptions. In short, we have a data set and we want to make sense of it. We would like to understand, for instance, which structures are in the data set. We want to try to validate some hypotheses that we have about distribution and information. We want to try to understand how many dimensions map to each other, how they correlate, and eventually identify which are relevant to our task. We have many, I would say, data visualization tools for exploratory data analysis. You can see some recent examples here. And in this case, you can see that they're mostly web-based and single user. Generally, it is hard to build something for exploratory data analysis in general, because it is a very broad field. There are too many algorithms, there are too many ways, there are too many paths to arrive to the same solution. And in this sense, it is hard to build deep enough general purpose tools, also because you generally need some domain expertise. You generally have something that's very specific to the task at hand that you need to do. And another problem is generally reproducibility. That is what I call getting lost in IDA. Generally, data scientists or data analysts try many different ways to arrive to a solution, and it's generally difficult to trace back how they arrived to that solution. Another difficulty is collaboration, because as I mentioned, most of these tools are actually a single user. A quick note here, when I write very broad field, it also means that it encompasses many types of data. For today, we are mostly going to focus on tabular data, so like structured data. However, this is an AR/VR conference. So the question here is, how can we use AR/VR to improve exploratory data analysis? And here I'm going to give a very brief background in immersive data visualization or visual or immersive analytics. You see 2 timelines, one for head-mounted displays, one for immersive environments. Here the idea is that with AR/VR, we generally try to see if depth clues, perspective, larger amount of space, because normally it is kind of cumbersome to handle certain data and fit it on a 2D screen. We can see if these things can be helpful for exploratory data analysis. This presentation was originally in Keynote, so we are going to see some unexpected animations eventually, so prepare for it. So we start in the 1965 with Ivan Sutherland, and we have the first prototypes, and in this case you can see how headsets are limited by the hardware at the time, and you can see these bulky prototypes. On the other hand, in the 90s we had the introduction of cave systems. Pretty much, probably all of you know what a cave system is, but I would say it's a cube on which like 5 faces have projections, and generally this is used with stereoscopical 3D to visualize 3D or spatial data. In the early 2000s, with the drop in the cost of LCD panels, we observed what we can call power walls or large display walls. And in this case, we have much higher resolution, but generally with the decision of sacrificing 3D rendering. Later on, with the introduction of what sometimes are called hybrid reality environments, you can have both 2D and 3D information at the same time. For us to have like some developer kits for headsets, we had to wait until 2013 and 2016 for the HoloLens. And at that point, the question is, what's going to happen between these two timelines, headsets versus immersive environments? At least for my personal work, what we introduced was data space in 2018, which we presented at IEEE VR this year, where we try to combine immersive environments with augmented and virtual reality headsets, so as to have 2D information for high resolution statistical information, and AR/VR for 3D rendering. Then the question here could be, what's going to happen next? Definitely we are seeing a boom in headsets. We know a bit less of what's going to happen to immersive environments, but that's a different story. So now that we have all these fancy AR, VR gadgets, so how can we actually use them to improve exploratory data analysis? And as we said, we can have different types of contributions. Normally, when you do exploratory data analysis, you want to see many things at the same time. You want to have context, you want to have detail, you generally have many different tabs, and it's generally hard to keep them all at the same time during the analysis. So a possible contribution is having a larger working space. At the same time, arguably, we can have a better interpretation of higher dimensional data, collaboration, and personalized analysis. So for instance, everyone could have its own slice of data and eventually see it from a different perspective. However, we have a big challenge. So pretty much this challenge is the current hype in VR, AR technology. So you can often hear advertisements about, oh, we are going to show you this amazing 3D scatter plot in your HTC Vive, and you're going to magically make sense of your company data. Or we can see very, simple or naive research papers where you can see 20 data samples, you see 10 participants, and then they say, oh, this is much better in AR, VR than in real life. The truth is that exploratory data analysis is very complex, and it's hard to boil it down to these simple things. So that's why throughout this presentation I'll try to pinpoint how deep we need to go and be rigorous in terms of analyzing the advantages of AR and VR. So again, while, sorry, I have little voice today. So while it has been demonstrated in various cases advantages of VR for certain tasks, it is still a bit unclear how AR/VR would perform in the context of ADA at large. So what we try to answer today is, which level of immersion would EDA benefit from? Would it be good to have a HoloLens? Would it be good to have a cave? Should I have an HTC Vive? And can we quantify how much AR and VR are actually useful? And finally, how can we design a fully fledged analytics system that seamlessly integrates AR and VR? So this is why we present our system called Immersive Insights, and we are going to propose a user study to discuss a bit more about these questions. I'm going to do a very quick introduction about data space. That is the system that we built Immersive Insights on. We call it a configurable hybrid reality environment. Hybrid reality because we have 15 high resolution displays to show statistical information, where you generally have dense text or charts that actually require high resolution. On the other hand, we have 3D content through HoloLens and Magic Leap devices. And then we have a table at the center where you generally have aggregate information, and that's mostly to foster collaboration. We call this concept like flexible data immersion, because in data space you can go from having a full virtual reality experience with a VR headset to having just a table and a physical environment. So you can sort of move across the virtuality spectrum. again, mini background on how this thing works, because it's a slightly of a complicated system. To make it short, it has a 3D model of the environment itself. So it's pretty much like a 3D model with the tables, the screens, and the lights, and where they are in space. We have 8 Kinect V2 sensors that create a point cloud, and then we detect where people and objects are in the environment. And then we overlay this with the mesh created at runtime by the HoloLens. And pretty much, this allows us to know where a person is with respect to other people, with respect to a screen. So for instance, I could say, okay, do this action, and this action is going to happen in the screen next to me because the system knows that I'm next to the screen. Similarly, if a person is speaking, we can rotate all the content or move the physical screens next to this person and so on. I'm not going to talk much about them in this presentation, but as you can notice, the screens are actually connected to robotic arms. So you can actually move screens physically next to people. So this is an example image in which we have a virtual representation of the environment. And on the top, you can see how an AR user would see a remote participant, and at the bottom, how the remote participant would see the experience remotely. So let's see if we can show something a little bit about the video. So very quickly, so Immersive Insights, again, is an application built on top of data space. It's actually a web application, so it's mostly done with React.js, WebGL, and the usual Python, scikit-learn and co as a backend. As you can see, we have statistical information on the screens that we call data views. Then we have a central AR area where we generally have one or multiple scatter plots of high-dimensional data. And then we have the table. Let's start with the data views. Since I don't want to make it like a system manual, so I'm going to go very quickly over these things. But few design notes are, for instance, the concept of data instance. Normally, on a 2D screen, there is not enough space to handle too many subsets of the data at the same time. The concept of data instance, for us, it is you have a subset of the original data samples and data dimensions. You apply your clustering, projection algorithms, and metrics to this instance, and this is what defines an instance. So it's pretty much a slice of data that you're operating independently. And through colors, you can operate on multiple of them at the same time, enabling parallel analysis from multiple data scientists. Sample data views that can be loaded through voice or other gestures. The table view, the projection, clustering, distribution, correlations, feature selection, feature filtering, and feature engineering. The table view, a bit more interesting, is the way we try to make people work together. So generally, it's where you can see all the solutions and data instances you're working on at the same time, and you can discuss about the algorithms that you're using on them. You can say, oh, I found this insight in this subset of the data. Oh, does it hold for the other part of the data? Let's put them together and see if this hypothesis holds. This is fundamental also for keeping track of the data instances. So on the table, for instance, you can see, I want to know data table is green, so it's associated to the second solution. I'm going to check the data table on the table, look up, and the screen for the data table is going to be in front of me. So it's useful for finding where my data instances are, and at the same time for comparing solutions. Let's go quickly to the AR integration. So, as I said, we use AR to visualize scatter plots of dimensionally reduced data at the center of the room. As I mentioned earlier, a 3D scatter plot by itself doesn't do anything, and we wanted to we wanted to enhance this concept, and we added what we call projection axis. Our implementation is ProLines that we presented in another paper. And the idea here is that once you have multidimensional data, you generally lose the connection to the original data dimensions. So you need to find ways to understand how these data features are projected into space and how they make points stay where they are. Another, I would say, AR, VR convenient application that we had is the backward projection. The idea is that I can air tap or select a data point, drag it into space, and see how its feature values will have to be modified in order to accommodate for this change. To give an example, I have Italy, I have a data point corresponding to Italy, and I wanted to go closer to the cluster containing the United States. I would physically drag this point, and then the system would tell me, okay, Italy should probably increase spending in research by X millions. You should probably decrease spending in other things by this much. And this way I can generate, formulate, and validate hypotheses. At the same time, the interesting thing is that scatter plots of dimensionally-diffuse data are very quick for understanding the structure of the data, but they don't provide much information. And the good thing here is that we can see with our HoloLens the dimensionality reduction, and in parallel see the higher resolution statistical information on the screens. And the fact that the AR projection is at the center of the room allows us from any position to see both a higher level perspective and dig into the details. At the same time, we also try to have something more like information on demand and provide guidance to where you are. And we have speech transcription. We have, when you look at a screen or you're about to perform an operation, before you do that operation, it tells you what's going to happen in AR. And generally, there is too many things that you would like to show on those TV screens, but you don't have enough space. So generally, when a person goes next to a screen, they can get some feedback on the choice of the algorithms or some additional statistical information. And in certain cases, we have 3D UIs. So for instance, it's very typical to change quickly the number of clusters and see how they split and they merge. So we have like a slider where you can easily modify this parameter. How did we evaluate this system? So we had what I could call more of a pilot study, because we only had 12 data scientists, which is not enough to have some statistically significant results, but it's good to have some first insights. And we had two parts. The first one is EDA and virtuality continuum. The idea here is that we would like to see how much immersion do we need. And in this case, we had 4 individual tasks, so each person would actually do a separate task on his own. And in this case, we had a data set about Fitbit data. And the second part was a direct comparison, which are very rare in this field because it's very hard to find an equivalent for an AR VR tool for these things. A comparison with I would say, state-of-the-art clustering EDA tool. And the idea here is try to see if collaboratively one performs better than the other one. So for the first part of the study, we split participants so that some of them would work in different modalities. The first one was the physical environment. So no AR, no VR, just the space as it is. The second one added the integration of HoloLens devices. And then we completely removed the physical space, and we said, okay, this space is very expensive to build. Why don't we just get rid of it? Like, would it be perfect? We don't need caves anymore. We just have a $300 headset and that's it. I mean, maybe the HoloLens is a bit more, but the VR ones are cheaper. And so in this case, we have a virtual replica of the environment with the same exact functionalities, even though, for instance, touch is replaced by air tap and similar equivalencies. And then we finally have the VR version. So let's go here. So what happened? Again, these results need to be taken as like suggestions more than a scientific proof. But for instance, what we noticed is that hybrid reality concretely decreased the task duration. So it actually has a positive effect, it seems. But at the same time, AR and VR standalone version underperformed compared to all the other possibilities. And this gives us an idea that despite the excitement about the VR, we are still not ready to have these technologies replace existing technologies. Some of the reasons are interaction. So air taps, gaze-based pointing, ray casting onto the interfaces from the long distance, terrible idea. Generally, people prefer to use touch, walk to a screen and actually touch the screen. or use the keyboard, because in certain cases it's actually easier to use. For filtering, it's easier to use a keyboard. Since we are trying to leverage tasks in which you need to look at multiple data views at the same time, having a small field of view is really a problem, because I want to see this in combination with this, and then I see only a slice of the data points, and then I need to rotate my head continuously, and this is not really practical. At the same time, we generally say, oh, the resolution of these devices has increased a lot. That's still not enough for certain things. So for instance, if I'm looking from the mid-distance, a statistical chart, some text, something that requires more resolution, that's not going to work. So that's why there are still high resolution environments, caves and so on.
In this video, we quickly introduced the dataset participants for our user study.
Sorry, didn't know what was present. So the second part of the study involves a comparison with cluster file. Here you can see a quick example of how it works, but the idea here is, instead of having many tasks, we have one collaborative task, which is actually long and complex enough. The task was to try to identify from a data set of UPDRS scores for people with Parkinson's disease, which could be the phenotypes associated with it. So which is an open question. There is no solution to this question. And in this case, we tried to evaluate both the time performance, but mostly the insights. So if we go to the results, you're going to see that we actually did have good improvement in terms of time performance as a team. But I would say that the most interesting thing is that the insights collaboratively generated with this type of environment is actually a superset of the environments of the insights generated with cluster file 2. So in short, we could say that we had more insights and in less time. But this is due to a complex combination of different things, at least according to us. We had better contextualization. You could see more things at the same time. Normally, on cluster file, you could work only a few slices of the data at the same time, and then you could overflow the screen. The table helped a lot in terms of reproducibility, collaboration. There were less parameter changes, less trial and error attempts. But on the other end, we had some issues with the headsets. So their use was intermittent, and there was some discomfort. There were people saying things from, oh, it's going to ruin my hair, I don't want to wear it, to I could personally live 24 hours a day with a HoloLens on my head. But there were people that was, after 2 minutes, this is too heavy, which is something that personally, it's hard for me to understand because I don't feel this problem. But apparently it happens. And then there were super funny things, such as a guy did a Bloom gesture and it quits the application of the HoloLens devices. Plus some difficulties with text input and other factors involved in the HMD. So for instance, we noticed that people were supposed to take HoloLenses from the table and use them personally. Instead, one person would take a HoloLens and then say, oh, okay, and then give it to another person, which is something that we didn't expect. So I think it would be nice to follow up with a future user study in which we test more things and we go deeper into this. To close quickly, so we noticed that AR and VR have a potential to benefit various aspects of data analysis. At the same time, we noticed that standalone AR, VR experiences are not suited, at least at the moment, for replacing existing technologies. We still have hardware design interaction challenges, and we need to admit that certain tasks are much better done with a keyboard and a mouse. So in this sense, I think that our community should continue try to research appropriate ways to apply AR and VR to data science. And when I say this, I mean creating new interaction paradigms, avoiding things such as, oh, I used to do this on a 2D screen, I'll try to port the same thing to VR. Those things are not always going to work. So for instance, like we saw for the case of raycasting onto the interfaces. And however, in the meantime, I think that we should think of AR and VR as a complement to what already exists and try to develop systems that allow you some flexibility. So for instance, I'm a data scientist, I would like to write my code in Python, and then maybe in certain cases I would like to have a 2D type of visualization, and then maybe at a certain point I would like to dig deeper and wear my headset. So I don't think we should constrain people to use only AR or only 2D or only coding, but they should be able to pick whichever modality of interaction and visualization they want, depending on the type of data and their task. And I thank you for your time, and this is it. As Gan said, I recently moved to Apple, so if you want to know how this project unfolds, you can contact Mark Podlasek, which is the manager of the data space. And thanks again.
Thank you, Marco. We do have time to take some questions. Any questions from the audience?
Hi, looks amazing. Congratulations. Quick question on the evaluation, because maybe I missed it. You were evaluating with groups, right?
In the second part of the study, yes.
Yeah.
I skipped it because it was it's much easier if you read the paper because it's a bit intricated how we, because it is generally hard to evaluate it. I'm going to make it brief, but pretty much we divided people into groups based on what they call analyst archetype. So you generally have sort of different levels of, I wouldn't say experience, but different levels of how people approach problems. And they are divided into 3 groups based on that way, and either way they are balanced. For the first part of the study, they were just, for the results, they were grouped into archetypes, but everything was done individually. So we had 4 people perform in a modality, 4 people perform in a modality, and so on.
So they would do it individually and then communicate about the results. So I see maybe you have some insights on this, that this type of environment where you have big screens and a table would be good if they're looking into the problem and talking to each other at the same time. Do you have any insights if that's the case?
That's the second part of the study. Right. So the first part, the idea was just make them do single tasks individually and see what performs best in terms of technology. The second part was pick the one that performed the best, which was the hybrid reality version. We would have liked to do it for everyone, but we didn't have enough participants. And in that second part, there were actually 4 people around the table, and they were interacting with each other, and they were balanced in terms of archetypes, and then they would communicate with each other. And then you can see more about the rationale of like this user study design. But they would decide when the session was over themselves and say, okay, we are done with this, and then we would make them list the insights.
Thank you. Make sure to read the paper.
Thanks.
Any other questions? I do have a question. So I think overall the conclusion is the hybrid does help improve performance, but AR/VR alone is not yet enough for used independently. Would you see as the hardware advances in terms of resolution, field of view, and all those things, would it become more feasible to or suitable to use as independently, or do you still think there will be a value for having a physical display?
Okay, so I'm a bit torn on this answer because I personally, I come from a lab where they developed the CADE 1 and CADE 2 systems, and I have some particular affection for immersive environments. At the same time, by working on this type of environments, I always have issues in justifying them. Having people coming and say, oh, why don't you just use a AR/VR headset? I think there's been already big improvements. If you check one of my first slides, there is a pic taken from a startup called Virtualytics, which I think is doing a great job in this space, and even with the current technologies, they're actually doing some good product. I think that probably the next wave of devices is going to have better resolution. We are going to have to work more on text rendering, eventually try to find, as I said earlier, try to not just to copy-paste what we did in 2D, but try to find new ways to interact with it. So I think it is probably possible.
So I just want to follow up what you just mentioned, right? So you said that the big problem for the AR and VR users was the interaction actually with the interfaces, because people like the tactile thing of touching the screens and so on. And it's, of course, now it's the problem of the gorilla hands, or whatever we call them, air taps. But there is a new devices are coming on the market that will allow you to have a bit more tactile things. What would you reckon? How much this would affect your study, having a bit better interaction with the interfaces?
So that's perfect, and it allows me also to add a note. So for instance, if you check at the charts they made, again I said take them as a suggestion. So for instance, it is very hard to evaluate these things, especially in this case. You will see these results and you will say, oh, AR was terrible. But something that, if you read the paper, you will notice is that in this case, for instance, we didn't even we didn't have the HoloLens clickers. So we could say, how would the results of this study be if we had the HoloLens clickers? That would have removed all the problems that we had with the air tap gesture. So going back to your question, probably it will have, I would say, a relevant impact. So that's why I say that it would be nice to redo in a little bit this user study, maybe with more people, introduce more modalities, and have more modalities for all of them.
Actually, I think your setup is fantastic because these kind of scenarios, right? So just repeat the same experiment with this.
One last question?
Just a quick question. Curious, do you think that the types of charts and interactions that you had the users doing has a larger effect on how they interpreted the interfaces versus, I guess, the larger conclusion that the interface was better or less useful? I see a lot of different charts and different interaction types. I'm just wondering if having so many different ways of interacting has had some effect on the conclusion.
So it's a bit of a hard question to answer. I think definitely yes in a way, but it's hard to estimate how much. Meaning that pretty much the interface for Immersive Insights has been inspired by the cluster file tool, which we knew it worked well internally at IBM. And in that case, you would use much fewer views at the same time, and the way we would use it was different in a way, because you would never have so many things at the same time. You would never interact with so many things and contextualize at the same time. So I would say that this is sort of experimental, and there might be some bias in how the results show based on the user interface design. So I think that if I had to do this a second time, I would probably reiterate another time on the UI design.
Okay, thank you. Please, let's thank the speaker again. Thank you. The second paper in this session today is from group from Victoria University of Wellington and University of Lisbon and University of South Australia. The title is Adventures in Hologram Space, Exploring the Design Space of Eye-to-Eye Volumetric Telepresence. And today we have Dr. Rafael Kofner dos Anjos as a presenter. He is a postdoc researcher at Computational Media Innovation Center at Victoria University of Wellington, and he received his PhD in Information Systems and Computer Science at Técnico Lisboa. His current research interests are real-time rendering, 3D capture and reconstruction, image-based rendering, virtual and augmented reality. So, thank you.
Thanks for the introduction. Hello, good afternoon. My name is Rafael. This is titled my paper, Adventures in Hologram Space. We're focusing on exploring the design space of an XY volumetric present experience. So, first of all, why am I talking about holograms? Why is this even a relevant problem nowadays? So first, just to make it clear, when I talk about holograms, I'm not talking about the special print that you have on your credit cards. I'm talking about the sci-fi representation of holograms. So for the rest of the presentation, I'll use that word, talking about this. This is Arnold Schwarzenegger in Total Recall in the 90s. So holograms, as we know it from sci-fi, have been very popular in pop culture, being as a 3D recording that you can see, ephemeral and out of thin air. Also recently, Blade Runner, you can see as a gigantic AI figure, or a reconstruction of an Elvis Presley show. In Kingsman, it has been used in sci-fi as a communication media through a very modern, that we wish we had, AR headset. But also Star Wars, right? Star Wars used a lot of holograms. In this case, we have a recording of Princess Leia. Also, they're talking to Obi-Wan here, another miniaturized hologram, a portable hologram where Commander Cody can talk to Palpatine. Also here as a remote conferencing technology where we have someone that is not there. Master Sifo Dyas is sitting on his chair in the Jedi Council. And also AR, portable AR technology with Cortana in the Halo series. In fact, it's such a popular thing that has its own page on TV Tropes. And the first sentence summarizes it very well. A staple of speculative fiction, holograms can be created by technological, magical, or physics means. Anyway, not only talking about science fiction, holograms are already starting to happen in our days through several research papers. Here we can see a floating head in this SIGGRAPH paper from 2009, where through specialized display, you can see a hologram inside. People using 3D glasses in front of a big wall. You can also have the sensation you're talking to a hologram in front of that wall. Through AR headset with his Microsoft research paper, holoportation, father can see his own daughter. If you see in the corners while he sees this ephemeral hologram, sadly she doesn't have a headset, so she can't see her father back, but if she had one, they could communicate. Through video projection in a specialized position, people can also have a sensation that they're talking to a hologram, even though it's a 2D image, because it's perspective corrected. And very recently, there's a Nature paper about actually producing a hologram out of thin air on tip of your fingers, but they're still very small. And there's a lot of work on projecting on mid-air displays with vapors and everything else, but the bottom line is they're now not only science fiction. Holograms are already in a reality in our days, maybe not as portable and effective as science fiction, but we have to look at them, right? So what is the problem? What am I trying to address today? So this is one example scenario that is popular where someone has a miniaturized hologram in his hands and wants to talk to him. What happens is, soldier here is looking down when he's talking to his hologram, and on the other side, he's looking forward. So what happens is, the soldier on the right is talking to someone that is looking down, is looking to his chest, and on the other hand, the hooded figure Palpatine is talking to someone who's looking down. So we don't have eye contact here. Eye contact is completely lost due to the miniaturization of that hologram. And this is something that happens in a lot of movies, and it's typically corrected by movie magic, where when the scene cuts, the character is looking to the other side. Well, so if we're using full scale, it's not a problem. It works, and it has been seen in this work, Room to Room, from 2016. If we're using a floating head, we can just place the floating head right in front of your face, and it will also work. But if we need to miniaturize, which is a very useful use case, this 2018 paper where AR headset user can see a miniaturized version of a remote person to provide remote assistance. Or let's say you want to have teleconferencing with someone on the top of your desk and you don't want it to be a huge person, you want it to be the adequate size. Eye contact is lost. So how can we ensure eye contact in this situation? So I'll quickly go to some of the functions of eye contact, which I think it's an important discussion to bring to the AR community, especially in this session we're talking about collaboration. We need to talk about why is eye contact even important in communication, especially in remote communication. So there's a lot of things in psychology talking about why eye contact is important. I picked 4 topics that I believe are very important to also remote communications, and I'll go through each one of them with some level of detail. First one is turn taking. This is an example scenario where we have 3 people talking, and by their eye contact, you can clearly see who's speaking. There's a guy in his back, because both of the others are looking at him. So through eye contact, we can clearly know who's speaking right now. Also, indicate a presence of a third person. If this guy suddenly looks away, everyone knows there's in this case a fourth person. Fourth person walks in the conversation. So, especially in a remote scenario, you don't have awareness of your partner's environment. You need to have proper eye contact to know if they're talking to you or if they're talking to someone else that just walked in the room. Moreover, turn taking, there are more subtle cues that can inform us about turn taking. People tend to look up and away right before speaking and right before finishing their sentence. So if you think about it, when you want to say something, you might look away a little bit and then look at the person and say, because it's a very subtle cue. And in this case, we can again see that the guy with finger in hand is talking. Both of the others are looking at him. When he finishes speaking, he might make eye contact again. And the guy on the left is probably signaling he will start speaking. So these subtle cues as well will facilitate people understand when it's my turn to speak. Is the other guy done or not? Yeah, this is the guy who is in control now. Second thing is information seeking. This is a scene from Brooklyn Nine-Nine, a TV show. I highly recommend it. Detective Jay Peralta is interrogating a suspect, and through eye contact you can see how the information you transmitted has been received. So you say something, and through the amount of eye contact the person establishes with you, you can see how the message you just transmitted is received. In this case, he's laying out a very elaborate theory of how the guy committed a murder, and this probably indicates something. He's looking past Detective Jake Peralta. I won't spoil the rest of the episode because it's a really good one, but if we want to have use holograms in remote communication for more serious things than just talking to someone in a gimmicky way, if we want to use it for interrogation, interviews, dating, or something else, we need to know how our information is getting to the other side. Third topic is cooperation, likeness, and social status. Through the amount of eye contact that people establish when they're talking, you can see if they're cooperating or competing. You can see how much they like each other, and also some differences in social status. The superior guy has a certain amount of eye contact than the underlying, maybe an employee and a base level talking to a CEO. In this case, an example of a job interview where clearly we can see that this guy is enjoying the candidate. He's saying like, oh, you're saying something very interesting. He's looking attentively to what she's saying, so indicates likeness. So again, this needs to be in remote communications to make it useful. Finally, the nature of the topic. This is a more subtle one, but it's known that people establish more eye contact when they're talking about straightforward issues. So talking about work, people will look at each other in the eyes more when they're discussing work than if they're talking about personal issues. Someone talking about something personal, they might look instead of looking to the other person, right? So from this conversation, we can see they're talking about some spreadsheets or something because they're establishing some high amount of eye contact. So also remote communication, we need to understand, is he talking about work or is he talking about some personal issues that I should pay attention right now? So bottom line is promoting eye contact in hologram-based applications. We will allow people to use these cues that they are used to in their day-to-day communications. So, without further ado, let's talk a little bit about how can we ensure eye contact in, let's say, any hologram-based application. So we define something called a hologram space, and with some variables that will go into some different use case scenarios. And finally, a simple approach to make sure whatever application you do, if you follow these guidelines, you'll have eye contact. So let's give this two locations, location A and B, with speakers A and B. The blue version here is the hologram, just so we keep in the sci-fi visualization so you guys clearly understand who's a hologram. Important variables are just the height of the user, a P, where is the position where the user currently is, and F being the track floor of where they are. So first problem is, let's say speakers A and B have this exact same height and they're in two remote locations, but one guy is talking to a hologram that is right in front of him on the floor, and the other guy is talking to a hologram that is on top of the table. So they're talking to a hologram positioned in different surfaces. What would happen is what we've seen before, they will break eye contact. And this is what we want, which is proper scaling to make sure eye contact happens. So in this case, the solution is pretty simple. We just need to downscale a hologram and the other space just enough to make eye contact using their height differences, right? So we just scale the other hologram up until my height, scale down. And on the other side, because we have the same height, I can just not do anything and we'll be looking each other into the eye. Okay, so solution will have A and C in this case. Problem number 2, what if we have a height difference between people? I will exaggerate here with the example of someone talking to their son, a little baby, but it's not very uncommon to talk to someone who's 30 centimeters shorter than you, which could also bring some sort of problems. So if I want to talk to my nephew, who's the baby, what would happen? On the other side, we have to highly scale this baby in order to make eye contact. On the paper, we call this the big baby problem. So what's the problem having a big baby? A big baby, their eyes would be widely separated from each other. How would I establish eye contact? I would have to go from one eye to the other. I don't know where to look first. Also, it's not natural. It's a gigantic baby in the middle of my living room. And so there are a lot of interaction things that wouldn't work properly if I'm talking to a giant hologram. Not talking now about a uncle-nephew scenario, father-son scenario. If we talk about a business meeting and we have a gigantic representation of our employee, we might feel like, oh, does he think he's bigger than me? Does he think there's a social status, like people attribute immediately to the size of the representation that probably comes from pop culture. If you think about Star Wars or other movies, the gigantic emperor that shows up and people bow down to it. So this might have some added weight of social status, which we want to avoid. So what do we do here? We just downscale enough the representation so we can keep the height difference consistent in both spaces. So if the baby was here, I would just have the baby on this side and downscale my representation on the other side to keep the height differences. So that would work. But that's not all. There's more variables that we have to consider, which is the third and final problem, is the relative position to the surfaces. So it's the same scenario now where we had someone here and other person talking to someone on top of a box or a table. If you walk away, just using the height differences won't make it. So our correction needs to go through using the angle that someone looks to the other guy in the other position, and make sure on both sides we keep the same angle. So this would happen. We use the angle that we should use, calculate how much we should downscale to keep the same viewing angle. I'll go into a little bit more detail, but basically the solution here is using an angle-based correction of height. Only talking about the scale. There are two obvious factors that we have to consider, which are if I'm walking around a tracked area, I should always be at the center of the hologram projection. So it's just a translation to the center, and also the users should always be facing correctly. So, and that's a simple problem to fix, where you just rotate it back to the, you see the rotation, the relative rotation someone has to the position where the hologram is positioned, and you just translate that to the other side. So if you look at the hologram on one place, on the other side you will be looking at the person. So this is a flowchart of the solution. It's a very simple solution, but I'll go into 3 cases that I believe is easier to understand. Simplest case is, first case, if we're able to downscale the remote user representation locally, and we know that the new scale will enable the other guy to downscale our representation, provide eye contact, we end the algorithm. So this is the case where the hologram is just taller than me, I can just downscale. A second case, which is this baby case, we have to check if we are able to downscale the remote user representation locally, but if we know that if we downscale their representation, we have to upscale our representation, we just scale using the angle base difference. So we don't force them to correct it. Final case, if we're on the other side, if we're not on the baby side, if we're forced to upscale locally to provide eye contact, we don't do anything, we leave it as it is, and we hope that on the other side, he will perform this operation. And we tested it. I'll show, this is a mock-up scenario, because this is the sci-fi scenario where we're talking to a hologram. You can recognize Daniel that's sitting right there. One of the co-authors of the paper is part of the video as an actor. Here is what you would see from the AR headset when you're talking to a hologram. But this is just a sci-fi view of it. This is the actual prototype that we built to test this algorithm, where we use OptiTrack cameras, method 2, HMD, just for the bigger field of view so we can see the whole body. OptiTrack rigid bodies to track the head position, and then OptiTrack rigid body to track the person, Kinect sensors to transmit the point clouds through a network. The holograms were in blue, this is just so you understand that's a hologram. We did a small evaluation where users had a quick riddle to solve, and then we would evaluate how well they communicated while solving the riddle. So first, on comfort in the experience, how well they communicated, we had considerably high scores. They could understand turn-taking and everything else naturally, so even using the teleconferencing solution, it was easy. We believe people are already getting used to Skype, so it also helps in doing turn-taking. However, regarding eye contact, we had very varying results. We had people that said we had a lot of eye contact, people say we had not a lot of eye contact. Why is that? So if we look at this guy that's wearing the exact headset that we use for the test, where is he looking? I would say he's looking this way, but it's fair enough if you say he's looking any other way, because you can see his eyes. It's a little bit reflective, the mirror. So this was, if you assume yellow, yes, you would answer, yes, we had a lot of eye contact. If you assume red, maybe not. We had pairs of people that after the study, one reported maximum in a 0 to 6 Likert scale eye contact, and the partner answered 1, no eye contact at all, and they were saying, oh, I was looking at your headset, and the other one, no, I didn't know if you were looking to the side where you had the headset. This is something that was already concluded by a 2016 paper from Cavallo, which will lead us to some future works remarks that we'll get in the next slide. But general remarks, we can say that scaling was in an adequate size to interact with the remote partner and use full body gestures. People showed inappropriate behavior. They had less eye contact when they're focusing on the problem and more contact when we're discussing topics. They had increased eye contact when they were laughing or agreeing about a topic, which validates the cooperation and likeness cue that we talked about. And overall, no problems in communication. Future work in this area, moving headsets from render avatars, it has been done, CREF paper last year. It is challenging still, it needs specialized hardware, it's not accessible to everyone. Using alternative types of visualizations might be a good answer. So no holograms with AR headsets, but with screens or real holograms. But if that's the case, these techniques should be as flexible as AR headsets in order to be valid. That's it from me. Special thanks to co-authors from Portugal that couldn't make it. Daniel is here. Other authors are close by, Australia, New Zealand, and I'll be happy to take some questions. Thank you.
Thank you. Any questions from the audience? It's really thought-provoking talk.
Thank you for the very nice presentation and citing a lot of new movies. I have a question, is that because I see in the picture where you show this user study scenario,
Yeah.
is that a scaling, upscaling dynamic? Is that because I think
it's dynamic.
So it's tracking the users and they will shrink whether
Yeah.
you're on table or on the floor.
Yeah, so we use the OptiTrack rigid body to check what's the position, and through the OptiTrack rigid body on the head, we know the height of the user. So they could pick up the marker, and it would scale and keep eye contact. For the test, we would leave it there. The way the user study worked, they had first time to just solve the riddle and talk about it, and during that time, the rigid body was there. We advised them not to touch it, so we could have a baseline where everyone's looking at the same place, same relative distance. And after that, we would have a more informal conversation where they were free to pick it up and talk to each other.
Okay, thank you.
So this image, is this, you said it, it's not blue, but this is use stereoscopic video for your avatars, or you use
Point cloud. Point cloud.
Point clouds. Okay, so
Yeah.
this is just like a mock-up thing.
Yeah, because the problem is Meta 2 HMD had it was really hard to capture what it was actually rendering. What it's actually rendering wouldn't match exactly what was in the mirroring that we got on the computer. So if we recorded what was in the computer, you wouldn't see any eye contact. So in this case, we use it's a mock-up of the situation. But what you would see would be more similar to this, but people having headsets. We just removed the headsets here.
And so you have some kind of negotiation between the two when you initiate the communication, who's going to see what, or exchange, so it sends the information on how big was the position of the avatar?
Yeah, so as I said, we know that you can only see one connect here. We had two connects like this.
Mm-hmm.
I don't know if that's the question. We would use two connects to cover the point cloud and avoid some occlusions from hand gestures. That's transmitted over the network, and we use a toolkit called the Creepy Tracker toolkit that we developed in our lab a couple years ago, which it helps calibrate everything and match positions with headset and different tracking systems.
We'll take one more question. Any questions from the audience?
Do you have any feedback about if people felt really small when they were like shrunk?
Yeah, so from the user study, people felt that the partner wasn't at an adequate size. We had a pilot study where we were not doing any scaling, so people were pretty small, and we noticed when people were really small, they would treat the remote guy as more of a gimmick, more of a toy. They wouldn't interact much with it. When it was bigger, so they would have eye contact, they would interact a lot more with it. But one of the future things we want to study is the big baby scenario. If size will have that sort of impact, but we need to do just a standalone study on that. If people have concerns of how do I look on the other side, or feeling that the other guy is misrepresented. But with this scaling that we use, that you can see in that one slide, people thought it was adequate. So no concerns on both sides. Sure.
Sorry. What about multiple avatars? If you show the two people scenario, so because there's the body rotation coming into place as well. So you thought about it?
Yeah. So that's future. One of the things we talked about future work is if we're talking on a multiple scenario, it would work. Just the orientation. If we just do the operation where we fix the horizontal plane rotation, but the scaling is something we need to look at. Because if they're widely different scales, we need to know how to represent the other guy. And that's one of the future work directions.
let's thanks the speaker again. Thank you very much. The last paper today in this session is from the HIT Lab, Human Interface Technology Lab, New Zealand, University of Canterbury. It's titled Exploring the Use of a Robust Depth Sensor-Based Avatar Control System and its Effects on Communication Behaviors. And we have Mr. Yuanjie, who is a PhD student at the HIT Lab. His research interest is in avatar-mediated interaction in VR by using multiple tracking devices. And the co-authors are Wang, Sungchul, Jung, Simon Hoermann, and Robert Lindeman. Thank you.
Thank you for introduction. So, yeah, I'm Yuanjie, a PhD student from HIT Lab. So today I'm going to talk about one of my research, exploring the use of robust depth sensor-based avatar control system and its effects on the communication behavior. So first, I would like to introduce some communication and avatar control system. So you know the verbal and non-verbal behavior are the two main components of the communication. It's very essential for mutual communication. So the verbal communication is a direct way we can use some words to express our thoughts, ideas to any other people. While non-verbal behavior, such as body language, can reduce the like misunderstandings, like through many forms like body posture or hand gesture, or eye contact, like eye blink or eye gaze direction, or even some facial expressions. So in the real world, we can present this communication through the face-to-face, or we can text or use some voice messaging or video chat. But in the virtual world, how we can do this conversation or collaboration? So if there is no avatar, so we can only use the audio or text message stuff. But if you want to have some immersed virtual experience, we need to have a digital representation in the virtual world to represent us. So the avatar is a digital representation. So if you want to have improved presence or user experience, we can use some like phone realistic avatar, like cartoon realistic or photorealistic. But that's not the part we are focusing on. The core research part we are focusing on is try to provide the users like a realistic behavior, like the full body tracking with hand gesture or even facial expressions. So for the avatar control system, it mainly consists two parts: data source and avatar control software. For the data source, the contact mode is a very popular way. Like if you want high quality full body tracking, you can wear the tracking shoes with reflective markers on or LED, and such as the optic track or face space. And of course, you can use a controller, just this controller and a headset. That's 3-point based this way to control the floating avatar like Oculus, Facebook space. And also, if you want to rendering more part of the body, like lower part or any other joints of the elbow, you can attach like Vive trackers as many as possible on your body, on your waist. And also you can use some contactless mode, like use some normal RGB camera or depth camera to provide the full skeleton. And and also once we got this all motion capture data, we need to find a software to map all the data to the virtual avatar. So we can use the inverse kinematic way. Excuse me. And once we can feed our track data, some joints into the software. Even if only had 3-point based data, like only two controllers and one headset, you can still, the system can presume that your lower body like working like in another way. We can, if you have enough tracking data, we can also use real-time calculate, like you can calculate the bone's direction and velocity of the king joints by calculate from the tracked king joints or mapped on the virtual avatar. So the existing problems about the avatar system in terms of data source. So if we use tracking suit, it's time consuming to set up and wear the different size of the tracking suit, and also it's very cumbersome. The price is usually not cheap, and we can simply use a controller, two controller and a headset. It's easy to use, but it lacks limited the tracking joints. If you attach more tracking sensors on the body, it's kind of like cumbersome. Of course, you can use some contact mode like on the depth sensor camera, but it has some occlusion problems. Like if your side face to the depth camera, one side like left side, your right side can be occluded by your left side. So and also you have the front and back ambiguity. Like the depth camera cannot detect which side you are facing to this camera, like front side or back side. And for the controller software, yeah. So if you have the IK software is not customizable, and if you have limited tracking data, the after control way is kind of like the accuracy is not high enough. So all these problems lead us to try to explore the questions: how different methods of the for controlling an embodied avatar support communication during the virtual environment in the virtual environment. So we set up this kind of a virtual interview and compare to different avatar control systems. One is the depth-based is our system, and also controller-based avatar control system to explore the effects on the presence, virtual body ownership, workload usability, and self-rated performance. So we presume that if we have the context way of tracking control the avatar, the user may have the higher sense of presence and all the body ownership, agency, sensory usability, and self-related performance. As in the controller session, the user need to use the controllers to press some buttons to perform some gesture, like point gesture. So we presume that the user may feel like higher sense of like a mental workload by using controller-based avatar control system. So we set up this depth sensor control, depth sensor-based avatar control system based on our previous work. So we place 4 connect data in the corner to transmit all the scaled data into the system and fuse all the data, so the users can move around and turn around in the tracking area without worrying about face any specific direction. We'll also integrate the deep motion sensors attached on the headset. So in this case, the users can have real hand gestures. As comparison, we set up this controller-based avatar system, use final IK, just use controller headset to rig the full avatar. So all the avatars were created by Hoermann, and we rendering the mouse movement using the plugins to like the mouse shape, like small, medium, and large based on the loudness. And also we aligned the gaze direction of the virtual character aligned with the HMD face direction. And also we used some random blink. You know, for every participant, they have different body size. So in order to fit into the virtual avatar we create, we auto-scale the size of the virtual avatar depend on the very first initial calibration. So we designed this virtual interview, and this user study contains 2 sessions. In the first session, the participant need to act as an interviewee, and the first task is to answer the interview questions from the interviewer, and all the questions were used and tested in the previous research. So the pictures on the right side, you can see the interview during the different conditions in the interview part from the first-person view, third-person view, and the real-world view. And in the first session, we have another task. The participants were asked to complete a road plan task. You can see the virtual map on the virtual TV. The participant need to work small steps close to a TV set and create a specific path from the red circle to the blue circle. And we expect that the users may perform some social cues like hand gesture or body gestures to conform the information to the interviewer. So during the interview session, we recorded every body movement, hand gesture, or facial expressions, and audio as animations. In the second session, we replayed all the recorded animation and asked the participant to review their own previous performance. Like we asked them to focus on the verbal and non-verbal behavior, so the participant can wear the headset and they can move around, turn around, and view and evaluate their own performance, like from a third-person perspective. So we recruited 25 participants, and they were aged from 18 to 35. We also asked them about the familiarity with VR and social VR. So we measure some dependent variables like presence ownership, presence using IPQ questionnaire, and body ownership agency, use an avatar embodied questionnaire, and for workload we use NASA text, and usability we use SUS questionnaire. So we'll also customize one questions for the self-related performers. So after we collect all the subjective data, we used paired sample t-test to analyze the data. So from the graph and the statistic table, we can find that actually there is no significant difference between the two avatar control systems on the presence and the workload. And we do find some significance between on the body ownership, agency, and usability, and some part of the performance, like only on the nonverbal behavior part. Yeah, for discussion part, we find this significant difference to support hypothesis 3 and 4, and we reject hypothesis 1 and 2. And we do find some limitation during experiment, like so as we fuse the data from multiple kinetics and lip motion, the single lip motion has limited tracking view. So when the participant move the hands around the front section, so the data may switch between lip motion and fused kinetic system. So they can sense this kind of like data switch during the review session. And also the participant may feel a little bit nervous. So during the interview, they put the arms too close to the body. So this may cause some occlusion problems recognized by the kinetic sensors. So from the third participant, we just ask them to be relaxed. So there's no body pressure effects anymore. So the conclusion part, we find significance, like higher virtual body ownership and agency, versus usability on our own depth sensor-based avatar control system. In the future work, we plan to integrate more lip motion tracking sensors on the headset to increase the hand tracking area. So we do not need to switch the data from fused kinetic system and lip motion system. And also we plan to add more like capture sensors to capture the facial expression and also the eye gaze recognition and integrate to our avatar system. So next I will show you the video about all the whole interview process.
Hi, this is a depth sensor-based avatar control system. So you can see this is my own body. This is my left arm, and this is the right arm. And also I have my fingers tracked by the lip motion sensor. And also my whole body is the data is coming from the multiple kinetics. So I can lift my legs and also I can walk. And if my arms are out of the tracking area of the motion, the data is coming from the multiple kinetics. See? Right. This is the controller-based avatar tracking system. So this is my left arm, and this is my right arm. And this is a simple point gesture. And I can move based on the HMD, and also can do something like this. But there's no leg movement.
this is
Hi, my name is. It's really nice to meet you.
Hi, nice to meet you too.
What is your greatest weakness?
Talking about my weakness, I think sometimes I'm a little bit lazy, so I always put everything stuff and get everything stuff ready in the last second. So this usually gives me a lot of time pressures, like when there is a deadline for the paper submitting or for the progress report. So I think I need to spend some time on the time management.
Okay, let's do the route planning task. You can see a map on the TV which covers the details of campus. You need to design the route from the red circle to the blue circle and explain why you planned the route that way. Okay, here we go.
Okay, sure. If we want to go from the beginning point to the end point, we can choose different ways. If we drive, we can take the main way and to take the University Drive and park our car here and walk through to this building.
Hi, my name is
review session.
It's really nice to meet you.
Hi, nice to meet you too.
What is your greatest weakness?
Sometimes I feel a little bit lazy, so I like to get everything stuff ready in the last second. So,
okay, let's do the route planning.
Hi.
My name is. It's really nice to meet you.
Hi, nice to meet you too.
How will your greatest strength help you perform?
In talking about strengths, I think it's concentration. So when I'm working on some like projects, coding or writing something,
campus, you need to design the route from the route that way. Okay?
on a road plan like this to from the starting point to the end point, I may choose different ways. Like if I drive a car or take a bicycle, I can take to this building. Nice to meet you too. It's concentration. Yeah, the starting point to the end point. So that's all. Thank you.
We still have 5 minutes for questions. Any questions from the audience?
Hi, thanks for the talk. Do you have any information about if people use the, because I see you had like a pointing gesture as well on the controller.
Yeah.
Did people use those as well?
Yeah.
Because I imagine like when they have their hands, they would like do things, but when they had the controllers, did they actually intentively do gestures when they were speaking, like pointing when they were speaking, or doing closing or opening the hand, or do it just open palms all the time?
So before the experiment, we told the participants that when they use the controller, they can only perform the basic hand gesture like opposite palm or point gesture or close. So during the route planning task, somehow they naturally use some like point gesture like, oh, I need to go from this point to this point, not perform like this way.
Okay.
So yeah.
What about when they were talking, like answering the questions? Do you notice if some users like decided to talk with their hands open or closed or pointing or something?
Yeah, we can't ask the participant to do the specific gestures.
Yeah, sure.
But they can evaluate their own performance in the review session.
Mm-hmm.
So they can see what the hand gesture they performed during the video, like the previous interview. So that's the reason we ask them to fill the questionnaire to evaluate themselves in terms of like non-verbal behavior they used, hand gesture or body movement.
Thank you.
I have a question kind of dovetailing what we were discussing just before. So obviously Vive hand controllers doesn't capture finger gestures, but some other controllers like Oculus ones does some basic hand gesturing. Do you think the results might have been different if even if they are holding a controller, being able to make more richer hand gestures, or would it be still considered as a bad motion?
I think if we customize more buttons on the controller, like use the trigger or touchpad to perform other fingers, that may like help the participant to perform more hand gesture. But I think for the basic task, the open and close and point gesture, I think the basic gesture can do the interview questions like a road plan is easy enough for this user study. I think if for some specific any other application scenario that may have influence, like more hand gesture.
Any other questions from the audience? If not, let's thank the speaker again.